Now the example is that we put a charge Q, a point charge Q, at the center of the K prime frame. So in the K prime frame, obviously, because it's at the origin, so it's not moving. So you know the field, right? So E prime is just the Coulomb field, right? You know that the Coulomb field is, but for us, we're using Gaussian. Following Jackson, we're using Gaussian. So for Gaussian, it's actually easy. You don't have the 4 pi epsilon 0, so it's Q over R QR direction. And we can choose to use a cylindrical coordinate, except this cylindrical coordinate has the actual direction along x. Doesn't matter. So you can see that R is, you can use R is rho in the rho direction plus x times x. Instead of z times z hat, now rho is just basically, in our case, it's y. I should say rho, z, z. Right. Okay, so this is a cylindrical coordinate, but with the choice of the actual direction a little different. But that doesn't matter. All right, so we can use that. This becomes Q, and actually everything is a point. Q, and this is rho prime in rho. Rho is in the x and y direction, and the unit vector actually it doesn't change because these are perpendicular directions. You don't need to worry about it's rho prime, it's rho hat prime or rho hat. The x change, the x hat doesn't change. Right? I just well, this is x and x hat doesn't change. Okay, divided by alpine q is just rho prime square plus x prime square d hat. Okay, now we know E prime, and B prime is 0 because it's electrostatic. All right, so we can now transform it according to using these rules. You can either use this set or that set, but for this problem, because these are all in vector form, it looks like easier to use this set. But except that now we want to find the electric field in K frame. We want to transform from K prime frame to K frame. And the transformation is easy. It's just basically changing beta to minus beta. It's the inverse transformation. Because K now is moving back with a minus V relative to K prime. So the transformation is just using these and changing beta to minus beta. Okay. And we want to calculate the electric field. And then because we can use this property if B prime is 0 in one frame. Once we get the electric field, the magnetic field is just beta constant. Okay, we can use what we already did in here. So we get the bay E. So we can write E this one. But bay these are pi. These are pi. But beta pi is 0, so you don't have that one. Okay, so you only have this one and that one. Okay. We'll combine the two terms a little. Let's just write it explicitly. So we have gamma, both have a gamma. Let's see what we should do here. Okay, let's just copy that everything is a gamma here. And then work this out a little bit, minus gamma square. And beta, you can use the fact that beta, so beta is just the same velocity because this this charge is moving, the whole frame is moving with velocity v, and v is the c beta in the x direction, or v x direction. Okay. So this is in the x direction. So beta in the x direction, which is just this one. And then this is beta dot e, so also get in the beta, also get in the x direction, the beta square. And we also have a q and x prime. This is in the x direction. Right? And the rest is the same. Oh, you have the gamma, as well. And then the rest is the same. Right? You can use anything. I think that's it. All right. So this is in the x hat direction. This is in, so we can separate the two, or let's see what we should do. We can get common factor out first. And for this one, it's just we get fine. And for the other one, both have the x prime. So x prime also go out for this term. So, x prime x. Yeah, x direction. Right. So what we have here is the first one is just one, right? We have gamma q all out, x prime, and all that out. The other is minus gamma. You have a gamma. You take one gamma, you have beta square, and then gamma minus gamma plus one, right? And again, you can use a multiply gamma divided by gamma q, and this becomes gamma minus one. And gamma square minus one is gamma plus one times gamma minus one, so you can cancel this with gamma minus one. And one minus gamma minus one. You can do a common denominator first. This is, or you can divide this. This is becomes one minus one plus one over gamma. So this is just one over. All right, so the whole thing is one over gamma. Let's just see, one over gamma. Okay, so all right. I think that's fine. You can multiply gamma and cancel this one. So it's here. Gamma will plus x prime z over gamma. I know the gamma quality cancel this x prime, this x prime, x, x, yeah. Okay, so the Jackson has an expression. Right. Oh yeah, over here. The Jackson's notations are difficult to follow. Well, let's see if this works out correctly. Not too much time, but let's continue over here. Now we are done with the transformation. So bring it down. So this is electric field in the K-frame, but then its expression is in the x pi and rho pi. So we want to express the field in the coordinate of K also. So we need to transform all this pi variable to the non-pi variable. For rho pi is easy. Rho pi is just the transverse components. Rho pi is just rho. Okay, so that is fine. For x pi, you need to do a transformation. So you can say that you want CT and x pi, x transform from x pi, or you can actually x pi to express that into the original one. So gamma minus gamma beta minus gamma beta gamma CT times x. And we only need the second one because so x pi is minus gamma c times beta, which is v times t, and then plus gamma x. Or you can say take the gamma out, so x minus vt. Okay, so not too bad. So we substitute everything here. Okay. Now the expression in the denominator is rho square plus this gamma square x minus vt half. And the numerator is gamma rho plus gamma, and then actually both have gamma plus x minus vt and x vt. Okay, I guess that's it. That's the end. All right, so we are almost out of time, or maybe already out of time, but just point out the property of this electric field, and also we can write down the magnetic field is beta cos E. So once we have that, we just beta cos beta is in the x direction. So x cos in the x will be zero. It's only this one. So x cos in the rho is the phi direction. Yes, okay. Rho phi divided by the same thing. There's a magnetic field associated with the moving charge. So these are the field of the charge moving with velocity in the K-frame. Okay. So the location of this, so whatever this location is v times t along x, right? So this is the location of the charge. At the location of the charge, both rho and x minus vt are zero. The denominator is zero, so that is reasonable. Both electric field and magnetic field will be singular at that location. That is due to the point charge. We assume a point charge, obviously. Near the charge, the field will be infinite. Okay. And the direction of the field, like the electric field, is simple actually, because it's the radial direction out of this position at rho is zero, x equals vt, which is the location of the charge. So this is the location of the charge. So all the electric field are still radially outward, the straight line out of the field. But then the intensity is not. The intensity is like the intensity along the perpendicular. This is the x direction. This is the parallel direction. The charge is moving with velocity v. When the perpendicular intensity or the E rho, E sub rho, as setting v equals to x equals to vt. So this is 0, this is 0. The magnitude is the gamma here, rho, and then actually divided by rho to p c half. And right, this is rho q square, right? So there's a gamma factor in here. But ex in this case, the parallel one is setting rho to 0. So this is 0, this is 0. And there's a gamma square in here. That is q divided by gamma square. I hope I got it correct. Yeah, square. Yeah. I hope I got it correct. Yeah. I think so. I hope so. But anyways, it because there's a gamma. If gamma is large or v is close to the speed of light, so E rho is much greater than EX. So this most few lines are in the perpendicular direction than in the parallel direction. So it's like the Coulomb field is uniform. The field line is also uniform, radial out. But for moving charge, it looks like the field are compressed along the perpendicular direction. There's a figure in Jackson also illustrate that. 11.9. Okay, so that is the property of this is the electric field, magnetic field for a moving charge with a constant velocity v. And you can get this expression by other methods. The method we did in chapter 6, or you can use something that in chapter 14. You can also calculate that, but I used to cover a little bit of chapter 14 because there has been a common question asking using material chapter 14, but I don't have time to this year. So if you want to look at that, I should have a video on that on Canvas. But that's all I can cover about this. Any question up to here? So this is how you do the transformation. So you have two steps. Once you transform the field from one frame to another frame, and the second step you transform the coordinate. Because once you transform from one frame to the other frame, you're keeping the old coordinate system. You also need to transform the coordinate back to the new frame from the old frame. Okay, so there are two steps involved in this process.
And while finding B, should there be a beta curve? Because it's beta cross T.
This one?
Yeah.
It's beta cos. Beta is in the x direction. Beta cos rho is the phi.
So should there be a beta?
Yeah, that's a beta. Yeah. All right. This depends on the velocity. Obviously, if B is 0, then V is 0, then it will be 0. Okay.